another quarantine day. To make it more exciting, we can learn new stuffs to our topic today. So our topic for today is an engineering subject, namely mechanics of deformable bodies or strength of materials. Before we jump into the tutorial, let us know what is mechanics of deformable bodies about. So what is it? Based on this book, Strength of Materials, 4th edition by Andrew Pytel and Ferdinand L. Singer, three fundamental areas of engineering mechanics are statics, dynamics, and strength of materials, or now we call it as mechanics of deformable bodies. Statics and dynamics are devoted primarily to the study of the external effects of forces on rigid bodies. Bodies for which the change in shape, or what we call deformation, is neglected. So in contrast, mechanics of deformable bodies or strength of materials with the relations between externally applied loads and their external effects on bodies. Moreover, the bodies are no longer assumed to be rigid. So to put it in simple perspective, here is an example. If we apply a certain force to this aluminum wire, it requires a certain amount of force to deform it or to bend it. So different materials have different strengths. This is what we're gonna learn today. For today, we will be discussing about strain. When you apply stress to an object, it deforms, right? Think of a rubber band, like this. You pull it and it gets longer. It stretches. Deformation is a measure of how much an object is stretched, and strain is the ratio between the deformation and its original length. Think of strain as a percent elongation. How much bigger or smaller is the object upon loading it? Just like stress, there are two types of strain that a structure can experience. First is normal strain. When a force acts perpendicular to the surface of an object, it exerts a normal stress or strain. Like this. If you compress it, compressive force, or you pull it, this aluminum wire is experiencing normal strain because you either compress or pull. There is no twist to it. On the other side, a shear strain, when a force acts parallel to the surface of an object, it exerts shear stress. So if I say twist it or pull it down, it exerts a shear stress or shear strain. So this is the problem we're going to solve today. A rigid beam with negligible weight is pinned at one end and attached to two vertical rods. One is bronze and the other is steel. The beam was initially horizontal before the load W equals 70 kips was applied. Find the vertical movement of W. So in order for us to solve any problem, we need to find the formula. So the formula of deformation is PL over AE, which P stands for force, L for length, A for area, and E for elasticity modulus. So in order for us to know or understand the forces acting on the beam and how to solve this, we must create a free body diagram. So let us redraw. The two rods of forces going upwards. Why so? Because it is the force that will resist the beam from collapsing and will become a counterweight for the load applied, which the force is going downward. But there is a pin on the side, so we can connote that it has two forces acting on it, one upward and one to the right. So after that, we need to assume how the beam deforms. In order for us to assume, we need to think that the whole body or beam will move, not just a single piece of the beam. So based on the illustration and the position of the load, we can assume that it will bend at the area which the load was applied, like this. It can't bend on which the pin is located because it is solid, right? So moving on. We can't just solve this problem directly because it has too many unknowns. So first, we need to find the forces acting on the rods. First, we need to get the summation of forces along y-axis. So, summation of forces equals 0, upward is positive. So 0 equals TB, or tension in bronze, plus tension steel, plus AY, the force in the pin, minus, since this weight is going down, so minus 70 times 1000, because we will be using PSI. So to make it more simple, TB plus TS plus AY is equal to 70,000. Next is we need to get the summation of moments. So summation of moments at A is equal to 0 counterclockwise positive. So 0 equals TB multiplied by 4, because 4 is the distance from the rod. And also the arrow will rotate counterclockwise, so it is positive. Same with the tension in steel. So plus TS multiplied by the distance, which is 8. So multiplied by 8. And also the weight, but since the force is going here and it will rotate clockwise, so it will be negative. Minus 70,000 times 12, which is the distance. So to make it more simple, 4TB plus 8TS equals 70,000 times 12. So that's it. Next is by ratio and proportion, so we can get the value of tension in the bronze and steel. So the value of deformation in bronze also over the distance, which is 4, equals to the ratio and proportion of the steel. So also the distance, so steel over 8. We can divide both sides by 4, so simpler, 2 deformation of bronze equals to deformation of steel. In order to get the tension, we need to substitute the formula of deformation in the equation we got. So from the ratio and proportion, the formula is tension equals PL over EA. That is the formula. So in order for us to substitute it here. So 2 TB 3 times 12, the length of the rod, but we multiplied it by 12 because it is in inches, over 2 times 12 times 10 to the power of 6. So equate this to also TS 10 times 12 over 0.5 times 29 times 10 to the power of 6. So using our calculators, we can arrive to TS is equal to 0.3625 TB. So now we have the value of the tension of steel. We can substitute it to our equation 2, which is derived from the moment. So 4 TB plus 8, 0.3625 TB is equal to 70,000 times 12. simplifying it, we will get TB is equals to 121,739.1304. So using the equation, we can also get the tension in steel. So using this equation, we can get the tension in steel. So this is the value of TB. So in order to get TS is equal to 0.3625 times the value of TB, 121,739.1304, we will get 130.43478. So this is the tension in steel, the force. So now that we have the tension or the force, we can get the deformation of any of the two rods. So let us try the deformation of the bronze rod. So the deformation is PL over EA. So now that we have the value, we can get the deformation of B. So if B, we have the force. So 121,739.304 multiplied by the length, which is 3 feet, times 12 because it is in inches, over area, which is 2 times the elasticity factor, which is 12 times 10 to the power of 6. So the deformation in the bronze is 0.1826. So by ratio and proportion again, we can get the value of the Y is a deformation in bronze over 4 equals the deformation in Y over 12. This is the distance from the pin. So to simplify it up, we have the value of this, right? So here it is. So 0.1826 over 4 equals Y over 12. So we'll move here. So Y equals 0.548 inches. So that is our answer. But in order for us to check if our answer, we can use the same process but using the deformation in the steel rod. So getting the deformation in steel is equals to 44130.43 times 10 times 12 over 0.5 times 29 times 10 to the power of 6. So we can get the deformation of 0.365, the deformation. But now we will use by ratio and proportion the same process. Use the steel over its distance. So 8 equals deformation of Y equals 12. So to make it more simple, 0.365 over 8 equals Y over 12. So Y is still, using our calculators, we can get 0.548 inches. So this is our answer. So that is all, folks. Thank you for watching and have a good day.